Today we're going to continue looking at derivatives and inverses. Specifically, we're going to look at the derivative of exponential functions and then at logarithmic functions, which are the inverse of exponential functions. So if you'll grab your calculators, we're going to figure out what the derivative of e to the x is. So I'm going to graph e to the x. And then I'm going to tell my calculator to take the derivative of that. So that's math 8. The derivative with respect to x of, you can either type e to the x or you can be uber lazy and do second trace, and y1 is right there. So graph the derivative of e to the x at x equals x. I have no idea what my last zoom was, so I'll start with a zoom standard. And there's my graph of e to the x. Apparently it's taken a, oh, it's done. Huh. There's two ways that you can see what's going on here. One is to, if I go back to this, and I say, all right, let's make this be a bold line. Maybe I'll be able to see it then. And tell it to graph again. And that bold line seems to go right over the top of the original. If we look at the table, you can see that for any value of x you choose, the original function and its derivative are, to many, many decimal places, exactly the same. Now remember that the derivative feature on here is estimating the derivative. It is never completely exact. But we can go down quite a ways and we're like, okay, again, those are to at least a couple of decimal places exactly the same. So it turns out that the derivative of e to the x is e to the x. It is the only non-trivial function that is its own derivative. There is a trivial function that is its own derivative. Do you know what that is? Something really, really, really simple. No, the absolute value, its derivative is either -1 or +1. Something simpler. What line? Y equals 0. Y equals 0 is a horizontal line, right along the x-axis. Its derivative is always 0, so its derivative is equal to itself. So that's a trivial function that has its own derivative, but e to the x is the only non-trivial one, at least that I know of. There may be something else, but the only one I know of that is its own derivative. So we can do problems like this by applying the chain rule to this. Here dy dx will be equal to e to the x plus x squared times the derivative of x plus x squared, which is 1 plus 2x. And there's really not anything that we can do to make this better, so we'll just leave it like that. The derivative of a to the x, where the base is not e, is a little bit more complicated. If we go back to the calculator, like, well, maybe they're the same. All right, well, let's go back to our y equals, and let's make this, say, 4 to the x instead of e to the x. And graph that. So here's the graph of y equals 4 to the x. And here's the graph of its derivative. And it looks like they're the same. But if we go to the table, we can see that they're not even really all that close when we get down to something like 4. This is 256, this is 254. My other one was exactly the same to multiple decimal places. Here they're not. So I don't believe that the derivative of 4 to the x is 4 to the x. Here's a derivation of how you can work this out. The derivative of a to the x is the same thing as e to the natural log of a raised to the x. Now, you may feel like that's a huge leap of some kind, but remember, e and natural log undo one another. So e to the natural log of a to the x is a to the x, because the e and the natural log undo each other. Then, using the property of logarithms that says the exponent on the argument can be rewritten as the coefficient on the logarithm, we can move this x out in front of here, and it's e to the x natural log of a. Then, taking the derivative of both sides, the derivative with respect to x of a to the x is going to be equal to the derivative of e to the something is e to that something times the derivative of that something. Well, we want the derivative of x times natural log of a. And remember, the natural log of a is a constant, like 5. So the derivative of 5x would just be 5. So the derivative of x times natural log of a will just be natural log of a. So this is the derivative of a to the x. The derivative of a to the x is a to the x times the natural log of a. So if you only wanted to memorize one rule, this would be the one to memorize. But we do a lot of ones with e, and so I would memorize this also. Notice I asked the question here, is this true if a is equal to e? Well, the derivative of e to the x then would be e to the x times the natural log of e, and the natural log of e is 1, because natural log and e undo one another, and the exponent on e there is 1. So let's do some examples, or an example. At what point on the graph of y equals 2 to the t minus 3 does the tangent line have a slope of 21? All right, so taking the derivative, dy dt, that's going to be 2 to the t times, because it's not e, natural log of 2. And I want this to be 21. Now, while you could put that into your calculator and graph it, you can also get an exact answer, and I feel like it's worth doing. If I divide both sides by the natural log of 2, I have 2 to the t is equal to 21 over the natural log of 2. Then what I do on these to solve it is I always use natural log. You can use other logarithms. Natural log of 2 to the t is equal to 21 over the natural log of 2. And it feels like, for just a second, that we've made it worse. Sorry. Didn't take the natural log on the right side. But remember, one of the properties of a logarithm is that I can take this exponent on the argument and move it to the coefficient. So that'll be t times the natural log of 2 is equal to the natural log of 21 over the natural log of 2. So then t is equal to the natural log of 21 over the natural log of 2 all over the natural log of 2. That's a lot of natural logs for one problem, isn't it? And you can put that into the calculator and give a decimal approximation for it. And we'll go ahead and do that. So I'm going to have the natural log of 21 over the natural log of 2 I guess I'll go ahead and put it in a parenthesis there, all over the natural log of 2. Is t equals 4.92 something, 4.921. And you could figure out the y coordinate if they wanted the coordinates. It says, when it says at what point, I'm always like, okay, what do you want? On the AP exam, they're really good about asking. If they want the coordinates, they'll say, find the coordinates. If they want just the x or just the t, they'll say, find the x coordinate at which blah, blah, blah. Your book frequently does this. They'll say, find the point. I always interpret that as give the coordinates, right? So to find the y on my calculator, the y is 2 to the t minus 3, so I'm going to have 2 raised to that answer minus 3. So that's 27.967. Questions about that? Okay, so now let's figure out what the derivative of the natural log of x is. If we start with y is equal to the natural log of x and use both of those as an exponent on e, I get e to the y is equal to x, because the e and the natural log being inverses undo one another. So then taking the derivative of e to the y, that'll be the derivative of x. On the left, we'll have e to the y times dy dx, and on the right, we'll just have 1. So then dividing, we have dy dx is equal to 1 over e to the y, and e to the y is equal to x, so we can do, that's 1 over x. So the derivative of natural log of x is 1 over x. That's another one that should go in your, here things that I have memorized. There's a lot of them for derivatives. I am going to show you the other derivation for this. If we let f of x equal the natural log of x, and let g of x be equal to f inverse of x, that's e to the x. Those two are inverse functions of one another. So then, by the derivative rule for inverse functions, f prime of x is going to be equal to 1 over g prime of f of x. Right? That's the derivative rule for inverse functions. That hopefully looks familiar to everybody. So that's going to be, well, the derivative of e to the x is e to the x, so it's going to be 1 over e to the f of x. So that's 1 over e to the natural log of x, and e and natural log are inverses of one another, so that's 1 over x. To me, this is sort of the more natural way to do it. This is the, what tricky algebra thing can I do to make this work? This is just using the derivative rule for inverse functions, which we're familiar with already. And then I say it should not be surprising that the derivative with respect to x of the log base a of x is 1 over x times the natural log of a. And I have students who go, why is that not surprising? Well, it's because log base a of x is equal to the natural log of x over the natural log of a. So that when I take the derivative of that, the natural log of a just stays down there. It's a constant. And then the derivative of natural log of x is 1 over x. Yes, ma'am?
Is the ln the thing next to x and c?
Yeah, that's natural log. I'm sorry, are you asking, is that an ln? Yeah. Sorry, my handwriting on those sometimes just all kind of comes out as a little squiggle. So let's look at an example of that. A line with slope m passes through the origin and is tangent to the graph of y equals natural log of x. Find m. This is a problem that one like this showed up on the AP exam several years ago, and students didn't do great with it. So now it's in a lot of calculus textbooks. So we've got the graph of y equals natural log of x, and the natural log function looks like all the other logarithmic functions. It looks sort of like this. And I've got a line that is tangent to this that goes through the origin. Where the slope of this line is m. Now, this point that it goes through has coordinates x, natural log of x. And the key is understanding that there are two different ways to find the slope of that line. One is, well, find the slope of the line. The slope of that line is going to be equal to the change in y over the change in x. So that's natural log of x minus 0 over x minus 0 is natural log of x over x. The other way to find the slope of that line is to take the derivative. So the derivative with respect to x of natural log of x, which is 1 over x. And a lot of students saw one of them or the other, but not both. And then we need to figure out what m actually is, so we need to know what x is. So I'll set those two equal to each other. Natural log of x over x is equal to 1 over x. The only way that's going to be true is if the natural log of x is equal to 1. And what do I take the natural log of and get 1? E. So our slope is 1 over e. And then one thing to be careful of, don't confuse the power rule with exponential rules. So this particular problem is not an exponential problem. This is just a power rule problem. Now, it's a little ugly. We normally have integer or simple fractions for the power, but pi is a constant. So the derivative of this is going to be pi times 2 plus sine of 3x raised to the pi minus 1 power times, because this wasn't just x, the derivative of 2 plus sine of 3x. Sine of 3x is itself a composite function, so the derivative of sine of something is cosine of that something, times, because of the chain rule, the derivative of that something. So this would be 3 pi cosine 3x times 2 plus sine 3x raised to the pi minus 1 power. Okay, any questions about that? Okay, then that's it for today.